So welcome back again. In this lecture, I will show you how to design a beam for shear by using SP16 as well as IS456. So this is the beam I am going to design it for shear. So this is beam 25, beam number B25, and beam size is 380 by 600. So first let me see the shear force diagram. So in combination, you select 1.5 dead load plus 1.5 live load. So for shear, you select shear 2 2. So apply, close. See here, for this beam, so at the supports, so magnitude of shear, it will be 139.56 kilonewton. Okay. See here, first beam size, 380 into 600 millimeter. So grade of concrete, FCK. So it will be 20 Newton per mm square. So grade of steel Fy. So it is 415 Newton per mm square. So and effective depth of the beam, it is 540 effective depth of the beam. So my shear, so at this location, so shear force, it is 139.56. So factored, it is factored shear Vu equals 139.56 kilonewton. So let me convert this value to Newton. So it is 139.56 into 10 power 3 Newton. For the same beam, in previous lecture, I demonstrated how to design flexure reinforcement. So you please go back to that video and please you revise it. So from that PT, so that is flexure reinforcement provided. So it is 0.39. So 0.39%. So in first step, let me calculate nominal shear stress. So nominal shear stress is nothing but shear stress due to shear force nominal shear stress is nothing but shear stress due to shear force that we are getting. So nominal shear stress, which is denoted by tau V. So for which I will refer IS456. So clause number 40.1. See here. So nominal shear stress. So tau V equals Vu divided by Bd. So Vu is shear force due to design loads. B is width of the member. D is effective depth of the member. So let me note down the equation. So it is Vu divided by Bd. So this is as per IS 456 2000. So clause 40.1. So it is in page number 72. So let me substitute the values. So tau V equals, so your VU factored shear force 139.56 into 10 power 3 Newton. So divided by width of the beam, it is 380. So multiplied by effective depth of the beam, so it is 540. So let me calculate it. So VU 139.56 into 10 power 3. So divided by 380 into 540. So this comes out to be 0.68. So 0.68 Newton per mm square. So this is tau V. So in the next step, I will calculate tau C max. It is nothing but maximum shear stress that the concrete can take. So tau C max is nothing but maximum shear stress that the concrete can take. So this tau C max, it is directly obtained from the code. So tau C max equals, so let me refer the code once again. So for which you need to refer table 20. Yes, here table 20, maximum shear stress tau C max in Newton per mm square. So in my case, grade of concrete is M20. For M20 grade of concrete, tau C max is 2.8 Newton per mm square. So tau C max, it is 2.8 Newton per mm square. So here in this case, so tau V is less than tau C max. So let me write it properly. So tau V is less than tau C max. Hence it is okay. Otherwise, you have to revise your section. If you get tau V greater than tau C max, you need to revise the section, which means you need to increase the depth of the section. So in the next step, third step, so let me calculate tau C, which is nothing but design shear strength. So I forgot to mention. So here tau C max, it is obtained from table 20. of IS 456 2000. So for tau C, again we need to refer IS 456 2000. So page number 73, page number 73. So table 19, table 19. So let me refer it again. So table 19. See this table. Table 19, design shear strength of concrete, tau C in Newton per mm square. So my grade of concrete is M20. Area of steel provided or percentage of steel provided, it is 0.39%. So here I need PT, percentage of steel. So it is 0.39%, and FCK, my grade of concrete is 20. So 20 Newton per mm square. See, for M20 grade of concrete, my PT, percentage of steel, is 0.39. So it falls in between 0.5 to 0.25. Okay, so let me record the values. So for 0.25, it is 0.36. So for 0.5, it is 0.48. So I need tau C for 0.39. So you need to do linear interpolation. So let me open my calculator. So X value is 0.25, 0.50. So for 0.25, 0.36, 0.48. Clear? So press on. So next, so shift 1. So you select a regression 5, again 5. So I need it for 0.39. So it is, so my tau C comes out to be 0.4272. 0.4272 Newton per mm square. So here tau V is greater than tau C. So let me recall the values. So your tau V value is 0.68, which is greater than tau C. Your tau C is 0.42. So both values are in Newton per mm square. So hence, therefore, shear reinforcement shall be designed. So it is required to design the shear reinforcement. So next step. So I think fourth step. So in fourth step, we know that my analysis shear, which is equal to shear taken by concrete plus shear taken by steel. So let me use the notations. So analysis shear is VU equals shear taken by concrete VC. So shear taken by steel, it is VS. So VU equals VC plus VS. Okay. So here you know the value of analysis shear and you can calculate VC from IS 456. So here VS equals VU minus VC. So I will show you how to calculate this VC. So VC equals, so you have the formula. So VC can be calculated as tau C into BD. Again, it is there in the code. So just later you can look into formula. VC equals tau C BD. So my tau C value is 0.42 multiplied by width of the section 380 and effective depth of the section 540. So VC comes out to be, see here, 0.42 multiplied by 380 multiplied by 540. So which is equal to 86184. 86184. It is in Newton. So to convert this to kilonewton, divided by 10 power 3. So VC, so divided by 10 power 3, which means 1000. So 86.184. 86.184 kilonewton. Okay. So here VS shear taken by steel, which is equal to analysis shear. So we know the analysis shear, it is 139.56 minus, this is 86.184. So shear taken by steel VS equals, so 139.56 minus 86.184. So which is 53.376. 53.376 kilonewton. So which means, so out of this VU, my concrete will shear 86.184. So remaining shear, it is shared by steel. Okay. So next, in the next step, we can calculate Vs divided by D. So which is your Vs is 53.376 kilonewton divided by D, effective depth. It is 540 millimeter. So if you substitute it centimeter, it is 54 centimeter. So let me calculate it. So 53.376 divided by 54, which is 0.98 kilonewton per centimeter. Okay. So once you get the value of Vs by D, so next step, so in the next step, you can refer SP16 table 62. So page number 179. Okay. So I think I have not opened the code. So let me open SP16. Yes, here. So in SP16, so table 62. Yes, here. So here it is, table 62. So shear for vertical stirrups, values of VU by D for two-legged stirrups in kilonewton centimeter. So my grade of steel is Fe 415. I am choosing 8 mm diameter. I am choosing 8 mm diameter. So my Vs by D value is 0.98. So 0.98 kilonewton per centimeter. So it falls here in between 0.9 and 1. See, first 0.907. So here Vs by D 0.907. You will get spacing. You will get spacing. So 0.907. Spacing it is 40. Spacing, corresponding spacing is 40 centimeter. So which is equal to 400 millimeter. So next value is 1.037. 1.037. So for which corresponding spacing will be 35. So for this 1.307, here spacing it is 35. So 35 centimeter. So which is equal to 300 millimeter. Sorry, 350. Sorry, it is 350 millimeter. But in my case, Vs by D value is 0.98. So my case, Vs by D value is 0.98 kilometer. So let me check the spacing for this value. Again, what you need to do? You need to do linear interpolation. So let me check it. So mode, first you select statistics. Number 2, see 0.907 and 1.037. So 40, 35. So on shift 1, so regression 5, again linear interpolation 5. So I need it for 0.98. So for 0.98, the corresponding spacing will be 37.19 centimeter. So I will adopt a minimum spacing, that is 35 centimeter. So here I used 8 mm dia, two-legged vertical stirrups at spacing 350 mm. Okay, so this is as per the design. So again you need to check this value with maximum spacing of shear reinforcement. Again you need to check this value with maximum spacing. So maximum spacing of shear reinforcement. So in my previous lectures, this step it has been already explained. So for which I will use IS 456 2000. So clause number 26.5.1.5. So that is page number 47. Page number 47. So according to code, so first spacing criteria is 0.75 times D. Next, second one is 300 mm. Next, third one is calculated spacing. So 0.75 times D means 540. So let me check it. 0.75 times 540. So it will be 405 mm. Next, second one is 300 mm. Next to my calculated spacing. So this is my calculated spacing. So 350 mm. So again, so out of these three, we need to adopt lesser value. So finally, corrected spacing will be 8 mm dia, two-legged vertical stirrups at 300 mm center to center. So this is my corrected spacing. Again, you need to check this shear reinforcement for minimum shear reinforcement. Whether you need to check it will satisfy your minimum requirement as per the code. See here. So next step, you need to check minimum shear reinforcement. So for which I will refer IS 456 2000. So clause number 26.5.1.6. Page number 48. Page number 48. See here, let me open my IS 456. So clause number 26.5.1.6. See here, this one. Minimum shear reinforcement in the form of stirrups shall be provided such that. So let me copy the same equation. So the equation is ASV divided by PSV, which is greater than or equal to 0.4, 0.87 F5. So just I will rewrite this equation. So which is ASV divided by SV. So greater than or equal to 0.4 times B divided by 0.87 Fy. So this is my LHS and this is my RHS. So whatever the reinforcement you provide, it should satisfy this requirement, which means your LHS should be greater than or equal to RHS. So first let me calculate the LHS. So LHS is ASV divided by SV. So your final shear reinforcement is 8 mm dia. So two-legged vertical stirrups at 300 mm center to center. This is your final shear reinforcement. So ASV means area of two-legged stirrups. So 2 into pi into 8 square divided by 4 divided by SV. Spacing you adopted 300 mm. So let me check this. So 2 into pi into 8 square divided by 4 divided by 300. So this comes out to be 0.33. So this value is 0.33, your LHS. So let me check RHS. So your RHS is 0.4B divided by 0.87 Fy equals, so 0.4, width of the section is 380, width of the beam divided by 0.87 Fy. So grade of steel is 415, so which is equal to so 0.4 into 380 divided by 0.87 into 415. So your RHS is 0.42. 0.42. So your code says LHS should be greater than or equal to RHS to satisfy your shear reinforcement. So in this case, your LHS is 0.33, your RHS is 0.42. So this condition has failed. So this is not greater than or equal to 0.33, which is not greater than or equal to 0.42. which means whatever you provided 8 at 8 mm dia, two-legged vertical stirrups at 300 mm center to center, it will not match your minimum shear reinforcement. It will not match your minimum shear reinforcement, which means you need to increase the amount of shear reinforcement. So to increase the amount of shear reinforcement, you need to revise the spacing, or you can increase the dia. So revise the spacing means you need to decrease the spacing, then only the amount of shear reinforcement it will be increased. So I will adopt new spacing, that is 225 mm. I will adopt spacing 225 mm. So my new shear reinforcement is 8 mm dia, two-legged vertical stirrups at 225 mm center to center. So this is my new shear reinforcement. I will check this with minimum shear reinforcement. So my minimum shear requirement is again ASV divided by BSV, which is greater than or equal to 0.4 divided by 0.87 Fi. So this equation can be rewritten as ASV divided by SV. So greater than or equal to 0.4 times B. So divided by 0.87 Fi. Again, this is my LHS. So this is my RHS. So first let me calculate LHS. So LHS is ASV divided by SV. So ASV is area of one stirrup. It include two legs. So which is again 2 into pi into 8 square divided by 4. So area of one stirrup. It is two legs. It is having two legs. So 2 into multiplied by area. So SV, I adopted the spacing as 225. So let me calculate this. So 2 into so pi into 8 square divided by 4. So divided by 225. So now your LHS is 0.44. So let me check RHS. So your RHS is 0.4 B divided by 0.87 Fy. Nothing has been changed. So 0.4 into B is width of the section or width of the beam 380 divided by so 0.87 Fy is grade of steel 415. So let me check this. So 0.4 into 380 divided by 0.87 into 415. So this is 0.42. See here. What is the condition? LHS should be greater than or equal to RHS. Here your LHS is 0.44, which is greater than 0.42. Now whatever the shear reinforcement you assumed or you designed, it is correct. So my final shear reinforcement is 8 mm dia, two-legged vertical stirrups at 225 mm center to center. So this shear reinforcement has satisfied the minimum shear reinforcement as well as maximum spacing of shear reinforcement as per IS code. So let me check the ETABS results. So let me check ETABS results. So I will run the design, concrete frame design, start design. See, design, concrete frame design, display, go to display design information. You select shear reinforcing, apply, OK. So this is the beam that I have designed. Here it is giving shear reinforcement area per meter. So 421.20 mm square per meter. So let me check this. So if you go to details, so shear steel. See here, it is mm square per meter, 421.20. So let me note down the answer. So 421.20 mm square per meter. So let me calculate the spacing. So this is my ETABS result. So let me calculate the spacing. So for spacing, you know the formula. Area of one stirrup in mm square. So divided by area of steel required per meter, and you have a conversion factor multiplied by 1000. So spacing S equals area of one stirrup. So 2 into, if you use 8 mm dia, 2-legged vertical stirrups. So 2 into, so pi into 8 square divided by 4. So divided by area of steel required, it is 421.20 multiplied by your conversion factor 1000. So let me calculate this. So 2 into, so pi into 8 square divided by 4. So divided by 421.20 multiplied by 1000. So it is 238.67. So it is the spacing required. So as you know, for shear reinforcement, the spacing will be provided in terms of in multiples of 25 mm. So minimum spacing will be 100 mm. Don't go less than 100 mm. It is very difficult to provide spacing at less than 100 mm at site. So next it will be 125 mm. So next 150 mm. So next 175 mm. So next 200 mm. Next 225 mm. So next 250 mm. So next 275 mm. So next 300 mm. So this 100 mm is minimum. Next, this 300 mm is maximum spacing. Okay. Here my spacing required is 238.67 mm. So I will provide so 238 means I will provide 225 mm spacing. Okay. So now you compare with the manual calculation. I think in manual calculation you arrived the same result. 8 mm dia, two-legged vertical stirrups at 225 mm center to center. So from ETABS results, you arrived the same spacing.